So in this video, I'm going to talk about linear speed and angular speed examples. I'm going to go through this whole list. So I have a whole bunch of different types of examples. And I wanted to do a bunch of different types because I find that these types of problems, I think that they could be a little confusing sometimes. So before I jump into these, and you can pause the video if you want to read what the problems are, but before I jump into these, I want to tell you some general hints that will kind of govern how we go through these problems. So first of all, when you read revolutions per minute or revolutions per second, this is really like omega in disguise. So you can multiply by 2 pi to get the angular speed. So the idea behind this is that omega needs to be in radians, not revolutions. So just to turn this phrase of revolutions per minute or revolutions per second into radians, just multiply it by 2 pi radians and you'll be there, okay? The revolutions will just drop out. It's not, revolutions are not like feet or inches, so it's something that can just easily drop out like that. Okay, the next hint is that when you read a problem and it's talking about traveling like a certain length, as it's going maybe around like a circle, within a certain time, you can view this often as arc length. So you can interpret this as S if you need to. And that's important because when you're working with these types of problems, oftentimes you aren't being asked to just calculate linear speed or angular speed. What you're actually being asked to do is to use the formula to solve something else. So you have to kind of pay attention to that and just keep in mind that any one of these formulas could be useful. So you, like I said, you might not be directly asked to use one of these formulas, but you need it to solve in the context. So I would recommend that you have these 4 formulas in front of you. And then the last thing I just want to bring up is that if the units confuse you, I think that's something that can be really tough. I suggest that you write them out and use dimensional analysis. I'm going to show you what I mean by that as we go through this video. So let's start with finding the angular speed of the minute hand of a clock if the hand is 8 millimeters long. So you want to consider when the minute hand makes a full rotation. So a full rotation would be 2 pi radians around, okay? So it makes that rotation of 2 pi radians in 60 minutes. This is kind of the way you want to frame things when you're thinking about rotations. You know, depending on the problem that you're working in, but since we're talking about a minute hand, we want to think about how long does it take to go that full rotation 2 pi radians. It takes 60 minutes for the minute hand to go around the clock, right? Okay, so now I'm being told to find angular speed. So this is a problem where at least I know exactly what formula I need to use. And I already have my theta and I already have my t, right? We just figured it out here. So I just plug those in. 2 pi over 60 and I get pi over 30 radians per minute. Now, as far as the units go, how would you have known that? Well, I know that 2 pi is in radians. I know that 60 is in minutes. So if you are really unsure about the units, you can just write that next to the terms so that you can really clearly see that you would get the radians per minute. Okay, next, find the linear speed of the tip of the second hand of a clock if the hand is 25 millimeters long. All right, so for this one, we want to consider when the second hand makes its full rotation once again. So maybe you just want to take a second to think about that. When does that second hand make its full rotation? It goes 2 pi radians in 60 seconds. Okay, so in this case, we're being asked to use linear speed, and we have these 3 different formulas for linear speed. So you just want to think about what information have you been given that will lend itself to which formula that you want to use, I guess. So in this case, I've got the radius, that's what this 25 millimeters is interpreted as. I've got a theta and then I've got a time. So in this case, it would probably make sense to think of linear speed like this formula. So I've got my v equals r theta over t. And so I can just plug in my information, right? So my radius was 25 millimeters. The rotation is 2 pi. That's the angle. And then it goes in 60 seconds. So this comes out to 5 pi over 6 millimeters a second. Okay, so let's just make that note on units. So what if you didn't know that? How would you figure that out? So here are my units. So if you are struggling with it, then you really do want to write these out. So whenever you have like a length and then radians, the length will always be the unit that you refer to. So if you don't have a length, then you can go back to using radians, but radians is not like... It's not like a length measure, so it's something that would normally drop out, okay? So when I'm multiplying millimeters times radians, the radians I know will drop out, so then I would just view this as millimeters per second, okay? So that's kind of the way that you think about that. And so then that's how I get to my millimeters a second. Okay, so next let's talk about this problem. So a bicycle has tires with a 12-inch radius. The tires are turning at a rate of 200 revolutions per minute. So how fast is the bike traveling in miles per hour? So this part here, how fast is that bike traveling? That's talking about linear speed, and this is going to take some work to get there. So the first thing that I want to do is I want to look at this revolutions per minute. So we talked about this at the beginning of the video, right? How many radians per minute is this? Well, I could multiply these together, right? 200 revolutions a minute times 2 pi radians. That's going to give me 400 pi radians a minute. And so, like I said at the beginning of the video when I gave you those hints, this is our omega. We can just now interpret that. So now we know that we've got omega. So you can now, just note this is talking about your angular speed, and you know it's going to be angular speed now because we've brought in 2 pi, so we've brought in those radians. You can always kind of think of it that way. And so now we can work on finding our linear speed. So I have my different formulas for linear speed, but there is the formula with linear speed that directly uses omega. So since I've found omega, this is probably the version of my linear speed formula that I want to use. So the rest of this now comes together pretty nicely because now I just have to take my radius times my omega, and I was given that we had the 12-inch radius, so this will just be 12 times 400 pi. So this comes out to 4,800 pi inches a minute. Okay, so just a note on the units here. So this was 12 inches, right? And then 400 radians a minute. So again, if you need to write these out to figure this out, don't be afraid to do that. So remember what I said. When you have like inches and radians, which one do you take? You will just default to whatever like the length measurement is. So I will now get rid of the radians and replace it with inches. So that's kind of the idea behind that, okay? All right, so now we need miles per hour, right? That's what we were being asked. I have inches per minute and I need miles per hour, so the problem's not done. So now I'm going to take this thing here, this 4,800 pi inches a minute, and I need to know just some other information. So I need to get my minutes into hours, and I need to get my inches into feet. So I'm going to tell you a couple of standard conversions that you're going to need to know for this. In 1 hour, there are 60 minutes. In 1 foot, there are 12 inches. And then in 1 mile, there are 5,280 feet. So this will allow us to go from minutes to hours, which is what we needed. And then to get inches into miles, so what I'm going to have to do is I'm going to have to convert from inches to feet and then feet to miles. So let's walk through what this is going to look like. So I start with my 4,800 inches in 1 minute. That's how I want to write out my conversion. So let's start with maybe the easier conversion. So let's start out with converting my minutes to my hours. So I want to use this conversion here to do that. And when I set this up, so I just want you to appreciate how I set this up. So I set this up so that my minutes are on like the diagonal. That's always kind of like, that's my visual way of thinking about this, is that I've got my minutes on this diagonal so that I can really easily cancel them out. So if with the way that fractions work, I can cancel out those units. And so what I want you to notice now is what's left over. Inches per hour. That is what we have converted to now, inches per hour. So I want to keep going with this. So now I want to convert my inches to miles, but what I need to do first is I need to use this information. So I'm going to go from inches to feet first. So inches is on top here. So when I set this up, if inches is on top here and I want to cancel this out, I need to use this conversion rate and put the inches in the bottom so that the inches can cancel out like this. And so now look at what I'm left with. I have feet on the top and hours in the bottom. So this is feet per hour. Okay, so now I need to use this last conversion. So I want to end up canceling out the feet. So notice that my feet are on top. Maybe you want to take a second to write out what you think the last part should be. Remember, math is not a spectator sport. You want to try this if you're struggling with it. Okay, so the last part of this is I want the feet to cancel out. So I use this 5,280 feet. I put that in the bottom. This will allow my feet to cancel out. And so look at what I'm left with. I've canceled out all of these different like conversions, and I'm left with miles on top and hours in the bottom. So I'm left with miles per hour. So now I just have to multiply all this stuff together. And really what this comes down to is 4,800 pi times 60 on the top. And then in the bottom, I'm left with 12 times 5,280. And so If I multiply that all together and do all my division and whatnot, I get 14.28 miles per hour. Okay, a pulley has a radius of 13.23 centimeters. It took 15 seconds for 45 centimeters of belt to go around the pulley. So first we're going to find the angular speed of the belt, and I want to focus on this part here. So it's talking about the amount of time that it took to go a certain distance. So I talked about that at the beginning of the video. This is talking about arc length. So we can think of this 45 centimeters. That is a distance. We can think of that as arc length in this problem. So that's helpful because this first problem is asking about linear speed, and I know I have these 3 different formulas for linear speed, but since I have identified that this piece of information here is s, that means I want to use this version of linear speed. So with that in mind, now I've got s divided by t. Well, we just said s was 45, and then the amount of time was 15 seconds. So boom, we're kind of good, right? So this comes out to 3 centimeters a second. And that units comes out because it was 45 centimeters in 15 seconds. So again, if you need to help yourself with the units, be generous with that. So next, I want to find the angular speed of the pulley in radians per second. And so now I can use there's a little bit of an issue here. So I could use my normal formula for angular speed, but there's another formula that I could use that I think is a little more convenient for this particular problem. So I've got V equals R omega. So why would I use this formula versus my angular speed formula? Well, because this is talking about linear speed in relationship with omega, and I have these pieces of information readily available. So from part A, I figured out V, and then I know the radius. So I can more easily figure this out than using the normal omega formula. So remember, I told you at the beginning of the video, another hint here is sometimes you will use the formulas in different ways to get the information that you need. So there's actually really 2 ways to get to omega. So in this case, since I know these, I can plug them in, and I've got 3 from the last part and then 13.23. So this is all I have to do to figure out my omega. So I can just go through that to get 0.23 radians a second. And if you weren't sure of why is it radians per second? So 1, you know that omega always has to be in radians. And then 2, so notice that on top here, this was centimeters per second, and I'm dividing that by centimeters. So my centimeters cancel out, which just leaves me with the radians. And for the last problem, so a thread is being pulled off a spool at a rate of 55.4 centimeters per second. Find the radius of the spool if it makes 155 revolutions per minute. All right, so we know how to interpret this revolutions per minute, right? So we can use this for angular speed, but we know that we need this in radians per minute. So to do that, I can just take 2 pi radians times that 155 revolutions per minute, and now I've magically got my omega, which is 310 pi radians per minute now. So that's kind of like a freebie. Now, one issue with this, though, that's a little tricky is that we are given this per minute, and this other rate is per second. So, see right here, per second. So that means that we're going to need to convert this to seconds. So I'm going to take my 310 radians per 1 minute, and then I'll just multiply by 1 minute per 60 seconds. So notice the way that I've set this up. I've got it so that the minutes end up canceling themselves out. That's really what's driving how you set up these conversions. So if I multiply these together, I get 31 pi radians over 6 seconds. So notice that I'm trying to leave this in a fractional state because it's just going to help give me a more exact answer towards the end. So I try not to convert to decimals until the very last moment. Okay, so now I've got my omega, and let's see, what was I trying to do? Okay, I was trying to find the radius, right? Trying to find the radius. All right, so this is one of those problems then where we're being asked to find the radius, not linear speed, not angular speed, but we have some information about like angular speed, and then we know that we have this formula here, right? So V equals R omega. So this actually will give us information about their radius. So this is kind of what I mean by sometimes you have to be a little clever with like which formula you're going to use. So I could plug in then my V, so my V was given, right? It's talking about the speed that it's like this thread's being pulled off. That is my V. So that's 55.4. We just found omega, and now I can go through what I need to go through to find the radius. Now, it might be helpful here to just include the units. So I've included the units here so I can do my dimensional analysis. So when I go to solve for r, I've got 55.4 centimeters per second. Notice I just rewrote this as a fraction. And then I had to multiply by the reciprocal, right? So to finish this, so I multiply by 6 seconds over 31 pi radians. And so in doing this, I can see that my seconds cancel out. And then remember, it's not going to be centimeters per radians. That does not make sense. You just say centimeters then. So the radians will just drop out in that case. Whenever you have one of those like official length measurements, then you can drop, say, in the radians. So this comes out to 3.41 centimeters now. And so that's it. Okay, so hopefully this gave you some good ideas of how to approach these types of problems. And thanks for watching, guys. I'll catch you in the next video.